This week we are going to talk about regression. Regression is a very useful tool that we can use to forecast, which we will talk about next week. The goal of regression is to explain the change in our dependent variable by varying one or more independent variables. Our focus is on the dependent variable or response variable, which is the value we are trying to predict with our independent or predictor variables. Scatter diagrams plot the independent and dependent variables. We usually plot our data before we perform regression to make sure certain assumptions are met and to see what kind of function might fit the data. Let's look at a quick example to see how regression works. Here, we want to predict our sales based on the payroll in a particular area. We plot our data points in a scatter plot, and then we try to find the line that best fits the points. We can see here that the line does not go through all the points, so it is not a perfect correlation between payroll and sales. In simple linear regression, we have our dependent y variable that we are trying to predict with our one independent variable x. What we actually do to find that line is to find a line that reduces the error term the most. We use something called ordinary least squares regression, or just simply least squares. We have to square the error terms to keep the error positive, otherwise the negative errors will cancel out the positive errors and it will look like we have less error in our model than we actually do. With regression, we actually are trying to find an estimate of a sample to help us better understand a population. When we start to apply our findings, the coefficient, which is beta 1 in this function, will become very important to our interpretations. Our goal is to minimize the square distance from our regression line to each point in our scatter diagram. We find that error by subtracting the actual value from our predicted value. This is the set of regression calculations used to find each of the values in our regression function. We can see here that with our regression function, we can take a value for our payroll and input it in for our x variable in order to calculate out what our expected sales are. When we determine the fit of our regression line, we can calculate some measurements of variability. The sum of squares total measures the total variability about the mean. The sum of squared error, which measures the variability of y about the regression line. And finally, the sum of squares regression, which measures the variability explained with our model. The bottom equation here explains how our three measures of variability are related. The sum of squares total is equal to the sum of squares regression plus our sum of squared error. The coefficient of determination, also called the R-square value, tells us how much of the variability of our dependent variable y can be explained by our model. The value can be ranged from 0 to 1, where 0 means our model explains no variability in y, and 1, where all of the variability is explained by our model. Ideally, we want our r-square value to be as close to 1 as possible. We use lowercase r for simple linear regression and a capital R for multiple regression. If we take the square root of our r-square value, we have the correlation coefficient, which expresses the strength of our linear relationship. Values for that correlation coefficient. 1, where there is a perfect correlation, a 0, where there is no correlation, in which we will have a horizontal line. A negative correlation coefficient indicates that we have an inverse correlation, and finally, any value between 0 and 1 will indicate a positive correlation. In order to use regression, we need to double check that our assumptions are met. The errors are independent. They are normally distributed, they have a mean of 0, and we have a constant variance. To check these assumptions, we usually look at a residuals plot. If all of the assumptions are met, then the residuals plot should look something like this and show a random pattern. Can see that the assumption for constant variance is violated, and thus regression is not a good model for this data. Other times, we may see that a relationship is not linear. And though linear regression may not be a good fit, other forms of regression, such as a nonlinear regression, might work, but we're not going to focus on this right now in this class. Multiple regression is performed the same way as simple linear regression. We just use more independent variables to explain the variance of our dependent variable. The mean square error represents our estimate of the variance and is calculated by dividing the sum of squared error by the degrees of freedom. Comes to after we developed our model and tested it, and we're ready to interpret what our actual coefficients mean with respect to what we're trying to predict. When we interpret the output of our regression analysis, we need to pay close attention to the statistical significance and the coefficients produced. The p-values indicate whether the values are statistically significant, and the coefficients describe the mathematical relationship between each independent variable and the dependent variable. P-values less than 0.05 are typically used to determine statistical significance. But what the test is actually saying is about the likelihood of finding a more extreme value. With respect to hypothesis testing, when we run a linear regression model, the p-value just tells us whether the correlation between our dependent variable and our independent variable is not 0. Often too much weight is given to the value of statistical significance. In essence, we are just verifying that the independent variable is associated with the dependent variable. Thus, statistically significant variables should remain in the model. Provide more detail about the relationship between the dependent and independent variable. The sign of the coefficient tells us whether there is a negative or positive correlation between the variables. This is probably the most important part of linear regression, is understanding how to interpret the coefficients. With a 1 unit increase in an independent variable, we will see the amount of that independent variable's coefficient increase in the mean value of the dependent variable, assuming all other independent variables are fixed. If we try to incorporate qualitative or categorical variables into our regression, we can use dummy variables. Basically, if we have a set of categorical variables, for instance, a variable such as insurance type, they could be grouped into different categories. Let's say Medicare, Medicaid, managed care, or self-pay. We can create a dummy variable for each of those variables where we would have 4 new variables in our regression model, and each one would be represented by a 1 if that category is true and 0 for all the other ones. So with the insurance example, if we're using Medicare, then for the Medicare variable we will have a 1, but we will have a 0 for each of the other 3 variables. To make sure we do not fall into this list of pitfalls when using regression. In particular, we need to make sure that all of our assumptions are met and we can proceed with regression, and that our relationship is statistically significant, but we need to make sure that the coefficients themselves have practical value for our analysis.